All right, we're going to start working through the quiz 12 answer key here. Now, there may have been some problems that are on this one that weren't on yours because there were a few different versions of this quiz. So if you see something that wasn't on yours, don't worry about it. That's fine. You just didn't have that particular question. But all the questions will be on here at some point. So just keep watching through, and anyone that was on your quiz will be covered on here. So let's start with this first one. We have a massless rod here, and we have a hanging mass attached to that massless rod and some force pushing up, supporting it. Now what changes is there are two different locations for the mass and for the force, but I'm just going to first start with this, thinking about my torques. In both situations, we can say that that force is providing a counterclockwise torque, doesn't matter where it's acting from. It's providing a counterclockwise torque regardless, and the mass is providing a clockwise torque due to the force of gravity acting on the mass. So what I'm going to do is I'm going to set up sum of the torques equals I alpha in both situations, and use that to figure out how those two forces compare. Because we're told that in situation A the force is F, okay? And we want to know what the force will be in situation B. So I'm going to start with situation A here. So the torques must be 0. So the torque from the force minus the torque from gravity must equal 0. Torque, we remember, is always going to be that RF sine theta equation. Okay, so we're going to be coming back to that equation as we sub in for the torques from each of those forces. And so the torque from the force, F on the end, is going to be L, the full length of the rod, all right, because that's where that force acts from, times the force, which has been defined as just F, times sine of 90, minus the mass, which acts in the middle at a distance of L over 2, times mg, also times sine of 90. That all equals 0. My sine of 90s just become 1, so they go away. And what I'm left with is L times F equals, moving this over to the other side, L over 2 times mg. The L's will divide out, and I find that F is just going to be 1/2 mg. So that's my original force. I'm now going to set up my new force when I switch around the locations. And so the basic setup is the same here for B. We can still say the torque from the force minus the torque from gravity equals 0. However, now L over 2 is the radius for the torque from the force. So that times F times sine of 90 minus L, which is where that mass is now, times mg times sine of 90. That equals 0. Sine 90s go away once again, and I get L over 2 times F, and I'm going to call it FB, the force in situation B, is equal to LMG. The L's go away, and I find now that the force of B is 2mg, which is going to be 4 times as much. So the answer there is 4F, because this new force, 2mg, is 4 times my original force, 1/2 mg. All right. For this next one, which is a similar problem, we once again are balancing some torques here. So now we have a uniform beam fixed to the one end of the wall with a hinge. The beam does have mass here. That's actually what we're trying to find. That mass, we're going to treat it as being in the middle, so the force of gravity is going to act in the middle there, creating a clockwise torque. And then we have the force of tension here, and creating a counterclockwise torque. So we once again can say the sum of the torques equals 0 for this situation. And so we can say the torque from tension minus the torque from gravity equals 0. So the torque from tension is going to be the full length of the rod, which I'm going to call L, times Ft sine of theta, where there's my angle there. Once again, I'm using this equation that I used in the previous problem. So that's the one torque minus the torque from gravity, which acts in the middle, so L over 2 times mg times sine of 90 equals 0. All right, I'm going to bring that over here, and so I end up with this sine 90 goes away because it's just 1. So I can say L times Ft sine of theta. Now that theta is not 90, equals L over 2 mg. Alright, now I can simplify and solve for m. The L's go away. I'm going to multiply by 2, so I get 2 Ft sine of theta all over g equals my mass here. And so my answer then ends up being, answer choice E here, 2 Fg sine theta, or 2 Ft sine theta over g. Alright, for this next set, the whole idea here for both of these problems is going to be that you must have balanced torques in order for something to balance. And so I'm going to start with this first problem here. We are pivoting about this point here. This meter stick is pivoting about that point. Now we do know it's not uniform, so the mass is not evenly spread out, which means we can't say that center of mass is right at the 50. We're told that it is not at that 50. So let's think first about what torques we have acting on it. So we have a torque from the mass on the right going in the clockwise direction. We have a torque from the mass on the left going the counterclockwise direction. Now, we know these two masses are equal. However, we can see that the R values are very much not the same. One is 40, one is 60. So we can say the torque from the mass on the right is going to be greater than the torque from the mass on the left. That means we need an additional torque of gravity going in the counterclockwise direction to balance. Okay, so we can say the torque from gravity must be counterclockwise. In order for that torque from gravity to be counterclockwise, it needs to pull down on the meter stick over here. Now exactly where it pulls we don't know, but it does need to create a downward force here to create that counterclockwise torque from gravity, which means, knowing that the force of gravity acts where the center of mass of the meter stick is, the center of mass must be here to the left of the 40 centimeter mark. We continue on to B, thinking about which of these situations would allow the board to balance, this non-massless board. And so once again, we're going to think about the torques from each one of these objects. So we're going to have a torque from gravity acting on the center of mass of the board, and a torque from the person. All right. In all cases, the torque from the person is going to go in the clockwise direction. So we need a counterclockwise torque of gravity to balance it. If we have our center of mass here, we're also going to have a torque of gravity going in the clockwise direction, so A is no good. If we have our center of mass here, our torque from gravity is going to be 0, so there's nothing to balance it with. But if we have our torque from gravity on the opposite side, that will create a counterclockwise torque, and that means that C is okay. So our correct answer choice here would be that only C would work. Moving on to our last set of questions here. It's really about just the basic ideas of conservation of energy, conservation of momentum, etc. And so the first question, we have a gymnast doing a front flip, and when they are in midair, they curl up into a ball, which causes their rotational speed to increase. And we want to know what explains this reason. So our first reason is the linear velocity is constant. That is not going to be true. We have an outside force from gravity here specifically, and that is going to mean that we will accelerate, and therefore our linear velocity will not be constant. Alright, so that first answer choice is incorrect. Second, angular momentum is conserved. This one is going to be true, but I'll go through the reasons why the other ones are not true in a second. So this one is true. And the main reason why we know angular momentum is conserved is we have no outside torques when we're in mid-air. Okay, the only force acting on the gymnast is gravity. Gravity acts at the center of mass, and therefore no torque is created. However, decreasing the moment of inertia does cause the angular speed to increase, and that just comes from our basic conservation of angular momentum equation. When we have a single object, we can say the initial moment of inertia times the initial angular speed equals the final moment of inertia times the final angular speed. So if the final moment of inertia decreases, the final angular speed must increase. Moving on to the next one, rotational kinetic energy is conserved. That is not true. For that one, we will have work done. Okay. The reason why work is done is there actually is work and energy required to pull the person into a ball. If you think about the situation we looked at when we first introduced some of these ideas, you had the person with the weights in the spinny chair, and their arms were all the way out. It takes work to pull those weights in. You have to exert a force over a distance to pull those weights in. And the idea is the same with the person curling up into the ball. There's work done, which means kinetic energy is not conserved. And lastly, linear momentum is also not conserved, and that's the same reason as answer A. There is an outside force, in this case from gravity, meaning the linear momentum will not be the same. All right, moving on to this next situation, we have a merry-go-round that's spinning around, and a child is on that merry-go-round, and we want to know what we can do to increase the angular velocity of the merry-go-round or the platform, and what correctly explains why that increase occurs. So for our answer choices here, the child can either walk towards or away from the middle of the merry-go-round. We know that we want to walk towards because that's going to decrease the moment of inertia. Moving away would increase the moment of inertia. And for this one, we're really thinking about conservation of angular momentum. And we can say that angular momentum is conserved because there are no outside torques in this situation. And so what we are thinking about is our initial moment of inertia times our initial angular speed equals our final moment of inertia times our final angular speed. What we want to do is we want to decrease that final moment of inertia. That means we are walking towards the center, and that will increase our final angular speed. So let's look then about our reasonings here. A says the total angular momentum of the system increases. That is not going to be true. We have no outside torques, and so the angular momentum will remain constant. The reason why the merry-go-round speeds up is we decrease the moment of inertia of the system. That increases the angular speed. All right, so let's work through the open-ended question here. So we have an object rolling down a ramp here, dropping a height of h from A to B, and then it rolls or flies through the air and lands on the ground down here. So let's think about what kind of energy we have at A. So at A, it's at rest, we're told. It does have a height, though, so it's going to have all gravitational potential energy here. When it gets to B, it actually dropped the height of h, but it's still a height of h above the ground, so it'll actually have half as much gravitational potential energy here, and that gravitational potential energy will have been converted to linear kinetic energy, as well as rotational kinetic energy. It's going to be both moving and rolling. It then flies through the air, and there's a really important thing that happens as it flies through the air, and that is there's no torque acting on it as it's flying through the air. We no longer have that force of friction that existed as it went down the ramp here. That force of friction is what made it roll. So as it flies through the air, we are going to have that gravitational potential energy go away. So we'll end with zero gravitational potential energy. But now, from B to C, all of that gravitational potential energy is going to become linear kinetic. And we're going to have the same rotational kinetic at C that we had at B, because for that period of time, there was no change in the gravitational potential energy. All right, now for part B, we want to derive an expression for the linear velocity at the bottom of the ramp, point B here. Before we do that, I want you to notice real quick that depending on which version of the quiz you had, you may have a slightly different object. Some people had a hollow sphere with a moment of inertia of 2/3 mr squared, and so I'm going to do this derivation using that moment of inertia. However, I will write down what the answers would be if you had either the solid sphere or the disk. The way you would go about it is the same, but the answers obviously would be slightly different. So we are going to use conservation of energy here. E initial plus work equals E final. We're starting with gravitational potential energy, and we're going to end with kinetic and rotational kinetic. Two things. Number one, no work's done because the torque from friction just goes into giving the object rotational kinetic energy. And the second thing is, for this particular problem, I'm going to say that this point right here at B is my 0 point. Obviously, we're still above the ground, but just to simplify it, I'm going to say we start at a height of h and end at a height of 0. You certainly, though, could say you start at a height of 2h up here and end at a height of h, and therefore you would still have some gravitational potential at the end, but I'm not going to do it that way. So plugging in what we know, we can say ug is going to be mgh is equal to 1/2 mv squared plus 1/2 I omega squared. Two substitutions I'm going to make here. Number one, I know that my moment of inertia for the hollow sphere, and again, yours may have been different, but for the hollow sphere was 2/3 mr squared. I also can say that omega is just v over r, so omega squared is v squared over r squared. So when I make those substitutions, I have mgh equals 1/2 mv squared plus 1/2 times 2/3 mr squared times v squared over r squared. Two important things happen. The r squareds go away, and there's an m in every single term that also goes away. And so I'm left with gh equals 1/2 v squared plus, when I do this here, 1/2 times 2/3, I end up with 1/3 v squared. Combining them, it's really 3/6 and 2/6, so it ends up being 5/6 v squared. And so I solve for v, and I get the square root of 6/5 gh. And so that is my velocity, my linear velocity at the bottom. Let's talk about what the answers would be if you had either the solid sphere or the disk. Alright, so if you had the solid sphere instead, you would have got an answer here of the square root of 10/7 gh. If you had the disk, it would be the square root of 4/3 gh. Let's go on to question C here. And so we want to derive an expression for the linear velocity of the object at the instant it reaches the ground, which is point C. So what I'm going to think about for here, there are a few ways of doing it, but I'm just going to think about my energy transitions from B to C. So once again, I'm going to say E initial plus work equals E final. I start with gravitational potential energy as I go from B to C. I'm now saying that my 0 point is at the very end here when we get all the way down to the ground at C. All right, and so that's why I'm now saying that we do have a height at B, but 0 height at C. And then at B, we also have kinetic energy and rotational kinetic energy, and then we're going to end with a final kinetic energy and a final rotational kinetic energy. However, I know that my rotational kinetic energy, and I see this from my bar chart here, my rotational kinetic energy has not changed from B to C. So in this case, those two energies are the same. All right, we have the same rotational kinetic energy in both situations, so they can just divide out. And so what I'm left with here is mgh for my gravitational potential energy plus 1/2 m times v initial squared equals 1/2 mv final squared. I do see once again that my m's will divide out, and I can sub in initial velocity, which will be the velocity I got here at point B. So what I end up with here is gh plus 1/2 times the square root of 6/5 gh, that quantity squared, equals 1/2 v squared, where v is that velocity we're looking for. So gh plus the squared and the square root obviously go away. And so 1/2 of 6/5 gives me 3/5 gh equals 1/2 v squared. I can combine those two terms, and I get 8/5 gh equals 1/2 v squared. I'm going to multiply by 2 and square root this, and so I get the square root of 16/5 gh equals v. So that's going to be my velocity at point C. We'll go ahead and put in those other answers if you had the other two shapes. All right. So if you had the solid sphere, for part C, you should have gotten an answer here of V equals the square root of 24 over 7 GH. If you had the disk for C, you should have gotten an answer here of V equals the square root of 10 over 3 GH. And so that wraps up C for all of them. Moving on to D, the question is now, the sphere, when it launches off the table, it travels a distance of x as shown. If the incline were frictionless, how would that value of x change? And the key really is if there's no force of friction, that means there's no torque, which means there's no rotational kinetic energy. So all of the energy that we started with, all that gravitational potential energy, would become linear kinetic energy, which means that at point B, okay, the sphere would be traveling faster. All right, it would have a greater linear speed at point B, which means when it launches, that horizontal launch velocity would increase. And since it's the same height, it's going to travel in air the same amount of time, but because it's traveling faster, it will travel further, and therefore that distance will increase. But the key really is that all of the gravitational potential energy now becomes kinetic, therefore it launches at a greater speed, but is in the air for the same time, so it travels further.